All right, today we're going to talk about the sum and difference formulas or identities for honors pre-cal here. And what we're going to do is I'm going to show you the proof. In your notes, I have listed, you've got a copy of this proof. But what I'm going to do today is I'm going to work it out by hand, and I just want you to follow along. All right, and it all begins with a picture, because I think pictures are worth 1,000 words. And I'm going to suggest to you that we have two angles, and I'm going to call one angle beta here and one angle alpha right here. And what we're going to do is figure out what the cosine and the sine of this angle, what that angle is. All right, so algebraically, what is that angle? Well, it's angle alpha minus angle beta. So this angle here is alpha minus beta, the one that I just drew. Okay, now knowing that that's alpha minus beta, I'm going to take this angle, alpha minus beta, and I'm going to rotate it and put it in standard position. And here it is in standard position. Okay, so all we've done is taken this angle and rotated it into standard position. So there you have it. So that's alpha minus beta. Now, when doing that, we have the distance between these 2 points is listed as D, and the distance between these 2 points is listed as D. And I hope you can see that those would be identical distances, because they are, all I did was take this angle and rotate it and put it in standard position. Now, let's talk about what this point is. This point is cosine of alpha, sine of alpha, because this is a unit circle with a radius of 1. This point here is on the terminal side of angle beta, and that's cosine beta, sine beta. Now, if I were to figure out what this distance was using the distance formula that you guys learned in geometry so long ago, I would take and say, all right, well, D equals the square root of, and it would be a long square root, x2 minus x1, which would be cosine of alpha minus cosine of beta, quantity squared, plus the sine of alpha minus the sine of beta, quantity squared. And since this distance is D, this distance is also D. So I could say that these two distances are equal, and I'm going to set up a distance formula for these 2 points. And this point here would be the cosine of alpha minus beta, because it's also intersecting here the terminal side with the unit circle. And this one would be sine of alpha minus beta. And thus the distance between these 2 points would be cosine of alpha minus beta minus 1 quantity squared, because that's x2 minus x1 quantity squared, plus y2 minus y1 quantity squared, which would be sine of alpha minus beta minus 0 quantity squared. And I'm running out of space over here, so I'll move that over. Okay. All right, and they're both the same distance, so these two quantities are equal to each other. So what I'm going to do now is expand the left side and the right side and see what falls out of that. All in an effort to find out what the cosine of alpha minus beta is. Now I do that because I don't want to, I want you to understand very, very much that the cosine of alpha minus beta is not as simple as the cosine of alpha minus cosine beta. It's a little bit more complicated than that. Well, a little bit more complicated, maybe a lot more complicated than that. But anyway, I like to do this proof so that you can understand that it is a little bit more complicated, and certainly is not that simple. All right. So since these two quantities are equal, I can square them and they will still be equal. And then I'm going to expand this left side here, and I'm going to go over here so I have a lot more space. So we're going to get When I expand this expression here, I'm going to get cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared beta. And now I'm going to expand this expression, which will get me plus sine squared alpha minus 2 sine alpha sine beta, using the expansion of a square of a binomial. And then this would be sine squared beta. Okay? Now I'm going to do one side at a time to have a little bit less confusion here and get all of this madness taken care of. And I'm going to ask you, do you see anything? Do you see anything wonderful that might happen? Well, I'd like you to notice that you've got a cosine squared alpha here and a sine squared alpha here. And cosine squared plus sine squared, regardless of what the angle is, they have to be the same. That's going to equal 1. All right, so that's 1. And then I have a cosine squared beta and a sine squared beta, and that also has to equal 1. And so right away, I have something that'll simplify down to 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta, which is really nice. And then I can factor out a 2, and I'm left with 1 minus cosine alpha cosine beta minus sine alpha sine beta. Close parentheses here. All right, and now we're going to expand the right side and see if we can find anything interesting going on there. All right, so when I expand this square of a binomial, we're going to get cosine squared of alpha minus beta minus 2 cosine alpha minus beta plus 1. And then sine minus 0 is just sine. And then if I square that, I get a plus sine squared alpha minus beta. All right, and looking at this side, I'm going to notice that I have a cosine squared alpha minus beta and a sine squared alpha minus beta, and that equals 1. And 1 plus 1 here is 2. So we're going to get 2 times, or 2 minus 2 cosine of alpha minus beta. And I'm happy to see that because I'm on the hunt for an expression for a cosine of alpha minus beta, and I can see that I'm getting closer here. All right, so now I'm going to factor out a 2, and I'm left with 1 minus cosine of alpha minus beta. And since I have 2's on both sides, I can divide both sides by 2 and get rid of the 2. And then I can subtract 1 from both sides, and that's going to get rid of these 1's. And then I notice that I'm left with negative cosine alpha cosine beta minus sine alpha sine beta equals negative cosine of alpha minus beta. And I see they're all negative, which means I can multiply everything by -1, and I will get all positive. And so I'm going to come up with this identity for cosine of alpha minus beta equals the cosine of alpha cosine of beta plus the sine of alpha sine of beta. And there is our identity for the cosine of a difference between two angles. Now, as I mentioned, it's certainly not as simple as just the cosine of alpha minus the cosine of beta. It's far more complicated over here. And I want you to notice a couple of things. The first thing is it's cosine, cosine, sine, sine, alpha, beta, alpha, beta. So it's cosine, cosine, sine, sine, alpha, beta, alpha, beta. And another thing to make a note of is that we've got a negative sign here and a positive sign here. So they're the opposite signs, SIGNs. And that's something to remember. So it's cosine, cosine, sine, sine, and the signs, I like to say, collide. And today in class, I had some students, Alec and Will, come up with they're opposite signs. And so to try to make it alliterative, you know, so we start with a C, we call them co-opposite, which was pretty funny, and it made my day. So co-opposite means they have opposite signs, or they collide, which means they have opposite signs. All right, so similarly then, if I have the cosine of the sum of two angles, alpha plus beta, I'm going to have the same situation, except now that I know that the signs have to be opposite. It's going to equal cosine of alpha, cosine of beta, minus the sine of alpha, sine of beta. And there we go. We have the cosine of a difference and a cosine of the sum of angles. All right, well, that takes care of the cosine. But what about the sine? Well, I'm going to make a little bit of a circular argument here, but hopefully you can go with me here. I'm going to suggest that we let alpha, I'm going to change alpha to another angle called pi over 2 minus alpha. Now, these two alphas are different, but I want to keep the alpha in the formula here. So I'm going to use alpha. I'm just going to replace alpha with this expression for another angle called pi over 2 minus alpha. All right, so I'm going to do that substitution in here, in this bottom expression here, and I'm going to say, okay, well, that's going to be then cosine of pi over 2 minus alpha plus beta, because just I'm doing a direct substitution here, equals, and then I'm going to do the same thing here. This would be the cosine of, taking the first angle here, would be pi over 2 minus alpha times the cosine of, excuse me, I'm going to write that better, the cosine of beta minus the sine of pi over 2 minus alpha, sine of beta. All right, and then on this side, I'm going to factor out a negative out of the last two. So I'm going to make this the cosine of pi over 2 minus, because I'm trying to eventually get to the cofunction identity to help me out here. So this is going to be alpha minus beta if I factor a negative out of the last two. And now this is going to be kind of my pi over 2, or it will be my pi over 2 minus theta, which we all know is equal to the sine of theta. All right, now this side here is going to equal, well, the cosine of pi over 2 minus alpha is just going to be equal to the sine of alpha using the cofunction identity. And then I have the cosine of beta, I'm not going to do anything to that, minus the sine of, the sine of pi over 2. Sine of pi over 2 minus alpha, well, that's just equal to the cosine of alpha using the cofunction identity. And then this is the sine of beta. All right, now this side, I know since it's a pi over 2 minus some angle, that's going to be the sine of that same angle. So this is going to be the sine of alpha minus beta equals the sine of alpha, cosine of beta, minus the cosine of alpha, the sine of beta. And there is the identity for the sine of the difference between two angles. All right, so now we have the sine of a difference of two angles. And what should we notice about this identity? Well, it's sine, cosine, cosine, sine. Sine, cosine, cosine, sine. And someone today said that that was a sine sandwich because we have the bread is the sine function and the cosine is the peanut butter and jelly, which I like. I like that a lot. So sine, cosine, cosine, sine. And notice here that the signs stay the same. Now, when I say signs, I mean SIGNs, stay the same. So sine, cosine, cosine, sine, the signs stay the same. And it's a sine sandwich, ha, ha, ha. We try to have fun with math when we can. All right, so here we go. So this is negative, but what if I want the sine of a sum? Well, the sine of a sum is going to be alpha plus beta equals, now, if these signs stay the same, we're going to put sine of alpha, cosine of beta, plus the cosine of alpha, sine of beta. And then we're done. Now we have the sine of a sum of angles. And that is the derivation using the distance formula and our unit circle understanding and angles in standard position for the cosine and the sine of a sum and difference of angles. All right. Well, good. Well, now we've got cosine and sine. We need to find the one for tangent. Yes, tangent. All right. Well, when we're doing our verifies, what we like to do with verifies typically is choose the more complicated side. But yes, I'm going to change it up a little bit, and I'm going to choose the less complicated side because I think I can expand this and make it look like this side a little bit more easily. All right, so we're gonna prove this or verify this identity. All right, we're going to start with what do we know tangent is? Well, tangent of an angle is equal to the sine of the angle over the cosine of the angle. So I can say that sine of x plus y over cosine of x plus y is equal to, and I'm just going to copy this down for the first time here so we can see where we're going. Okay. Now, I like to talk to you about what I'm thinking, even though when we're verifying, we're not allowed to touch the other side. We're not allowed to touch the other side, but I'm going to have a little thought bubble going on here. Here it is. I'm seeing this one here, and I'm thinking, here it is. There's my thought bubble. How do I get a 1 over here? Well, I don't know yet, so I'm going to expand this side using those two identities that we just came up with on the previous page. So the sine of a sum of two angles is going to be, as we remember, the sine of x, whoops, I don't need a parentheses here, the sine of x, the cosine of y, plus, because the signs stay the same, the cosine of x, cosine of y, all over the cosine of a sum, which is cosine, cosine, sine, sine, and the signs collide or are co-opposite. I can't even say it. This is cosine of x, cosine of y, minus the sine of x, sine of y. Now, I'm really happy to see the plus on top and the minus on the bottom here, because on my right side, I know I have to have a plus in the numerator and a minus in the denominator. And now I'm thinking, I got to get a 1 down here. And this term that is sitting in the 1 spot here is the cosine x, cosine y. So I'm thinking to myself, what can I do to this to make it equal 1? Well, I'm thinking that I can probably rewrite this and multiply it by a factor of 1 that's favorable to me to get a 1 over there. And I think this is going to be my factor of 1. Oops, that's an x here. Because what happens if I multiply this 1 over cosine x cosine y times this term? Well, I'm going to get a 1, which is what I want in that spot. All right, so we're going to take this left side here, and we're going to multiply it by this favorable factor of 1. Now, you might think, well, I would never have come up with that, Mrs. Muller. And I would say, that's okay. I saw somebody do it once. And now you've seen somebody do it once. And now that you put that in your little toolbox and you're happy. And say, okay, I'm gonna take that and run and do more of my own creating. All right, so let's multiply this in, distribute it in. We're going to say the numerator now will look like the sine of x cosine of y over this denominator here, which is cosine x, cosine y, plus cosine x, cosine y, over cosine x. Oh, wait, you know what? I made a mistake, didn't I? This is sine, cosine, cosine, sine. Whew. I'm looking at that going, that's not quite right. I didn't do my sine sandwich right. So this is sine of y up here. That's why I hesitated. I'm like, oops, something. I don't need a 1 here yet. Cosine of x, cosine of y. I feel much better about that. Sorry about that, folks. But to err is human, and I am definitely human. All right, so on the bottom here, I'm going to multiply this in, and I'm going to get cosine x, cosine y over the same thing, which is my glorious 1, which I need right here, which makes me very happy, minus the sine x, sine y, over cosine x, cosine y. All right, and now I'm going to look at my expression and see what we can do. Well, let's see, I have sine x over cosine x, cosine y over cosine y, and cancel those. That's nice. And now I have cosine x over cosine x on this term. I can cancel that out. And looking at it, analyzing it here, sine x over cosine x is, well, that's nothing but tangent of x. Plus, this is sine y over cosine y, which is tangent of y, all over 1 minus, this is tangent of x, tangent of y. And there we go. We have a verified, a scary looking identity for the tangent of a sum. And we say, boom, good proof. Okay, now, I have been known to put proof like this on a test, so I would kind of make sure I knew how to do this. And remember that the analysis is just knowing how to get a 1 on the lower left. And you could do the same thing with the tangent of a difference. You could do it with a cotangent and of a sum and a difference. And the only difference here where we were cotangent, you would use cosine over sine. And you would do something very similar. All right, so that's the tangent of a sum and difference. And notice that the sum and difference is, if you have a sum, the numerator has the same sign and the denominator has the opposite sign. And that helps me sometimes when I'm trying to memorize these things. All right, so let's do some examples or figure out why on earth we would be subtracting and adding angles in the first place. Well, this is why. Back in the day, we did not have these fancy calculators that would allow us to find the sine of 75 degrees by just typing it in the calculator and getting a number. We had to go and use a book and use trig tables. And I'm dating myself when I say this because, yes, I had to use some trig tables. But basically, it was just a table of values where if I knew the tangent of 75 is what I wanted, I would look for the angle of 75, and it would give me a 4-digit number that was the ratio of the hypotenuse, or the opposite over the hypotenuse, in a 4-digit decimal. And then I'd use my 4-function calculator and add, subtract, and multiply. So, but not all the time do you have a calculator. But we can figure out that the sine is equal to the sum of two numbers that we know standard values on our unit circle here. So 75, I can say the sine of a sum of two numbers here, or a difference. It doesn't matter. There are infinitely many combinations you can come up to get 75. The most common one is going to be the 45 and the 30. So I can say that the sine of 45 degrees plus the sine of 30, or plus 30 degrees, because this adds up to 75, is equivalent to the sine of 75. And now we can use our sine. I put these formulas up here for your reference. The sine of a sum here, this expansion, to figure out what the sine of 75 is without a calculator. All right, so let's do that calculation. So we're going to say this is the sine of 45 degrees because it's sine, cosine, cosine, sine, and the signs stay the same. So it's the sine of 45 degrees, cosine of 30 degrees, plus cosine of 45 degrees, sine of 30 degrees. And we all know what these values are. So the sine of 45 degrees is root 2 over 2. The cosine of 30 degrees is root 3 over 2. Plus the cosine of 45, which is root 2 over 2, and the sine of 30, which is 1/2. So we know that's going to equal root 6 over 4 plus root 2 over 4. So that's the sine of 75 degrees. Well, let's prove it to ourselves. Let's get our handy dandy calculator. Well, there it is. There's mine. Pulling this out here. Now, you'll notice I'm in radians, so I need to change my mode to degrees. You should be in degrees in your calculator too. And now I'm going to do the cosine or the sine of 75 degrees. Well, it gives me the same thing, but I want the decimal value. And with the decimal value is 0.9659. All right, and we can prove it to ourselves that this is equivalent. So let's just do second root 6 divided by 4 plus 2 divided by 4. Oops, I better put parentheses. Nope, that's right. We're good. We're good. And see if we're equivalent. And lo and behold, we are. So this is equal to this. And what's the cool thing about this calculation here is that this is the exact value and this is rounded because there are a whole lot more decimal places after that. All right. I am in the middle of recording and of course my dog comes home. So we're going to do the cosine of 75 degrees and that's going to be the cosine of, we can use 45 degrees and 30 again. So this will be the cosine of 45 and the cosine of 30, or we're going to add them together. And we're going to expand using the same formula that we came up with here, cosine of a sum. And that's going to be cosine, cosine. So cosine of 45 degrees, cosine of 30 degrees, minus, and the signs collide, the sine of 45 degrees times the sine of 30 degrees. And let's do some plug it in here. What's the cosine of 45? Well, that's just root 2 over 2. The cosine of 30 is root 3 over 2 minus the sine of 45 degrees, which is root 2 over 2, and the sine of 30, which is 1/2. And so then this turns out to be root 6 over 4 minus root 2 over 4. And obviously I say that's the cosine of 75 degrees. So we're going to see if that's equivalent to the cosine of 75 degrees on the calculator. All right, so let's put that in the calculator and clear this out. And we're going to go second cosine of 75 degrees. And we're going to go diamond approximate. And we get 0.2588. All right. And now we're going to see if our expression here is equivalent. So I'm going to go up and clear this and grab the old expression that I had up here and then just change this to a minus sign. And then figure out if they're the same. And you'll see that they are identical. They're the same number. Again, this being the exact number and this is a rounded number. So there is a lot of value in being able to know what the cosine of 75 is exactly. All right, now tangent. The good news is there are two ways we can find the tangent of 75, okay? The tangent of 75 is going to equal the sine of 75 degrees over the cosine of 75 degrees. And we actually know what those numbers are because we just calculated them. We know that the sine of 75 degrees was, if you look back at the top here, root 6 over 4 plus root 2 over 4. So let's put that down here. So that's going to be root 6 over 4 plus root 2 over 4 divided by, and then we just figured out what the cosine was, which was root 6 over 4 minus root 2 over 4. And if I were to multiply this entire expression by 4 over 4, I can get rid of the denominators, and I can get the square root of 6 plus square root of 2 over the square root of 6 minus the square root of 2. And through the magic of rationalization, this is going to be root 6 plus root 2, root 6 plus root 2. We get root 6 times root 6, which is 6, plus 2 times the square root of 12, plus 2 over, well, this is going to be root 6 squared minus root 2 squared, which is going to be 6 minus 2, which is 4. All right, so that expression is going to equal 8 plus, and I can take a 2 from under the root here, and we get 2 times 2, which is, this is 4 root 3 over 4. And this is going to be equal to 2 plus the square root of 3. All right, and if we use our handy dandy calculator, and we go second tangent, and I'm going to tangent 75, and I'm going to go and get the decimal, and if you can't see it here, it's 3.732. And if I say 2 plus second root 3, you'll see that they are identical. Well, that's good, that they are identical. And this is the exact value of the tangent of 75. Now, I mentioned to you that there was another way we can do this, and that is the tangent of a sum. Let me fix my camera here so I can have more space. I can do the tangent of a sum formula, which is the tangent of x plus the tangent of y over 1 plus the tangent of x times the tangent of y. That's the one we just, oh, this is minus on the bottom here, I'm sorry. Minus in the denominator, tangent of y. Okay, so let's say we want to find the tangent of 75 using 45 and 30, which we've been doing all along. So this is equal to the tangent of x plus y. So if we want the tangent of 45 degrees plus 30, which is the tangent of 75, that's going to equal the tangent of 45 degrees plus the tangent of 30 all over 1 minus the tangent of 45 degrees times the tangent of 30, which are all unit circle numbers that we should know. And I like tangent of 45 because it's a nice, easy number called 1. And so this will be 1 plus, and this tangent of 30 is root 3 over 3. And then we get 1 over 1 minus, and tangent of 45 is 1, tangent of 30 is root 3 over 3. All right, and I'm going to just eliminate the fraction by multiplying, or the double-decker fraction by multiplying by 3 over 3. And this is going to equal 3 plus root 3 over 3 minus root 3. And then we can rationalize that, and that will, I promise, yield 2 plus root 3 when you rationalize it. Okay, now we can do the same thing with radians. Radians, our favorite thing in the world is radians. But you're like, pi over 12, Mrs. Muller, pi over 12 is not a nice number. Well, you're right. And adding fractions, I know teenagers are all allergic to. And I hate to do that to you, but yes, sometimes we might have to find the sign of pi over 12 without a calculator. All right, now, but that's a little bit more difficult on the unit circle because we have increments here. We got pi over 6, pi over 4, pi over 3, pi over 2, and not any 12ths. So this is what I do. I change all my first quadrant and maybe a little into the second quadrant into 12ths. So that means I'm going to take pi over 6 and I'm going to multiply it by 2 over 2 to get it into 12. So I'm going to get 2 pi over 12. And then if I multiply pi over 4 by 3 over 3, I get 3 pi over 12. And then if I multiply pi over 3 by 4 over 4, I get 4 pi over 12. And then the 6 over 6 at pi over 2 gives me 6 pi over 12. And then this is going to be, if I multiply by 4, it'll be 8 pi over 12. So we have so many different angles now here. We can try to add or subtract to get pi over 12. So to get 1 pi over 12, let's use 4 pi over 12 and 3 pi over 12, which is in effect pi over 3 minus pi over 4. So I can say that the sine of pi over 12 is going to equal the sine of pi over 3 minus pi over 4. And I'm going to use the sign of a difference now, a formula, which will be the sine of pi over 3, the cosine of pi over 4. The signs stay the same, plus, and I just changed it, minus the cosine of pi over 3, sine of pi over 4. And we know these numbers on the unit circle. So the sine of pi over 3 is root 3 over 2, sorry. The cosine of pi over 4 is root 2 over 2, minus the cosine of pi over 3, which is 1/2, the sine of pi over 4, which is root 2 over 2. And so we're going to get root 6 over 4 minus root 2 over 4. Now this number looks very familiar. Well, believe it or not, pi over 12 is equivalent. This is radians. In degrees, this is 15 degrees, which happens to be complementary to 75 degrees, which means that the sine and the cosine values will be interchangeable. All right, so if we go on our calculator here and we change our mode to radians, here we go, changing my mode to radians, and I want to do the sine of pi divided by 12 and get a decimal there, I get 0.2588. And I'm going to remind you that if I go back up here and grab the root 6 over 4 minus root 2 over 4, we will get the same value. So it works. Okay. All right. So similarly, the cosine of pi over 12, let's do the same situation as we did up here. Let's say that that's going to equal the cosine of pi over 3 minus pi over 4. And it's a darn shame I can't pause, but I can't. I'm sorry. Anyway, so let's listen to the expansion here. That's going to be the cosine of pi over 3, cosine of pi over 4. And the signs collide, so this will be a positive, and then it's going to be sine of pi over 3, sine of pi over 4. So let's evaluate these numbers on the unit circle. So this is the cosine of pi over 3, which happens to be 1/2. The cosine of pi over 4, which is root 2 over 2, plus the sine of pi over 3, which is root 3 over 2, and the sine of pi over 4, which is root 2 over 2. So if we were to calculate this, we get root 2 over 4 plus root 6 over 4, which we say is approximately on the calculator 0.9659. If we go back up here and we grab it, if you look at it up here, well, I don't even have to do that. I'm going to change this to a plus sign. There it is, 0.659. And if I say, clear this out and do the cosine of pi divided by 12, we get 0.9659. All right. So the tangent of pi over 12, well, what is the tangent equal to? It's equal to the sine of pi over 12 over the cosine of pi over 12. And we happen to know those because we just calculated them. And so I'm taking the sine of pi over 12, which is root 6 over 4 minus root 2 over 4, over the cosine of pi over 12, which is root 2 over 4 plus root 6 over 4, multiplying everything by 4 over 4 to eliminate the fractions. I can get root 6 minus root 2 over, I'm just going to make this root 6 plus root 2 because it doesn't matter which order you put it in. All right, and if we were to rationalize this, we get root 6 plus root 2 over root 6 plus root 2. And multiplying I'm sorry, to rationalize it has to be negative. I have to use the negative because I have to take the conjugate of the denominator. All right, so this is going to be root 6 times root 6, which is 6. And then we'll have 2 times root 12 plus root 2 times root 2, which is just 2, over the bottom of the denominator is root 6 squared minus root 2 squared, which is 6 minus 2, which is 4. And then so this is going to be 8 minus 4 root 3 over 4. And then we get 2 minus root 3. And if I were to do the tangent of pi over 12, we get 0.269. Okay, and then similarly, if I were to go 2 minus second root 3, I would show you that that is the exact same number. Okay, and again, this is the exact number for the tangent of pi over 12. Now I just have been doing sine, cosine, and tangent, but I don't want you to think that we can only do those 3, because we can do the others exactly too. Because what if I asked you what the secant was of pi over 12? Well, the good news is we already have the cosine of pi over 12, which is this. And we know that the secant is nothing more than the cosine, 1 over the cosine. So this is 1 over the cosine of pi over 12. And 1 over, I can say root 2 over 4 plus root 6 over 4. And I can say this is 1 over root 2 plus root 6 all over 4. And then if I flip that fraction, I get 4 over root 2 plus root 6. And I'm not going to rationalize that. That would be the secant, and that's how you would do the calculation for that. Okay, so that's how we can use the sum and difference formulas to find the exact values of angles that are not our standard angles on the unit circle, but are a combination of the addition and subtraction of them. Okay, now another problem type you might get in these sum and difference questions is one like this, where you are given the sine of an angle and the cosine of another angle, and they ask you to find the cosine of the sum of the 2 angles that you were given. So the question states, find the exact value of the trig function given the following. Let's say we have the sine of u is equal to -7 over 25. What I'd like you to remember is that the sine is equal to the opposite over the hypotenuse, and the cosine is equal to the adjacent over the hypotenuse. All right, and the question states that both of these angles are quadrant 3 angles. So I'm going to draw these quadrant 3 angles. Here's the initial side, here's the terminal side, and I'm going to draw my angle U. And there we go, there's alpha. And since I know that the opposite is -7, this bottom here will be -7, and then my hypotenuse is 25. The adjacent then is going to be -24, because that's a Pythagorean triple. Now let's draw angle V. Here we go, here's angle V. This is also a 3rd quadrant angle, alpha. And this is V. And I have the hypotenuse is 5. The adjacent now is -4. And this is also a Pythagorean triple, which is -3. And now we're going to try to find the cosine of U, which is equal to the cosine of U, the cosine of V, using the expansion for the cosine of a sum. The signs are the opposite, and then this is the sine of U, the sine of V. Now, the cosine of U is equal to, well, let's look at this triangle over here, and that's -24 over 25. And the cosine of V, they were nice enough to give us, which is -4 over 5. So I'm going to replace that with this. minus the sine of u. Well, the sine of u is negative 7 over 25. And the sine of v is, I go to this triangle here and I see that's negative 3 over 5. All right, and if I were to multiply this out, I get 96 over 125. And I want you to notice these both have the same denominator. So this is 125. And then minus 21, because a negative times a negative times a negative is still a negative. And then that's going to be 75 over 125, which is 25 goes into both of these. So this would be 3 fifths. So the cosine of the sum of those two angles is equal to 3 fifths. The sine of the difference would equal the sine of u using the expansion cosine of v. The signs stay the same. Cosine of u, sine of v. All right, so we're just going to replace these with the values we find in our reference triangles up here above. So sine of u is going to be negative 7 over 25. The cosine of v is negative 4 fifths. Minus the cosine of u, which is negative 24 over 25, which is the adjacent over the hypotenuse. The sine of v is negative 3 fifths. So this is going to be 28 over 125 minus 24 times 3, which is 72, because we have a minus, minus, and a minus. And 72 minus 28 is 44. So this is equal to negative 44 over 125. Let's make sure I did that right. The sine of u is negative 7 over 25. The cosine of v is negative 4 fifths minus the cosine of u, which is 24 over 25, minus the sine of v, which is negative 3 over 5. And 24 times 3 is definitely 72. And if I subtract them, that's what I get. You can't really reduce that, so we're stuck with that. All right, the tangent of u plus v is equal to, if I use the expansion, it's the tangent of u plus the tangent of v all over 1 minus the tangent of u, tangent of v. The tangent of u, well, let's go to our triangle. The tangent of u is going to equal the opposite over the adjacent, which will be negative 7 over negative 24. So that's going to be 7 over 24. Plus the tangent of v, which is going to be 3 over 4, right? Because negative 3 over negative 4 is a positive number, so that's 3 over 4. All over 1 minus the tangent of u, which we just figured out, which is 7 over 24, times 3 over 4, the tangent of v. And 24 times 4 is 96. So I'm going to keep both of these denominators as 96, because I know that'll eventually cancel. So if I keep them 90, that's going to be 28 over 96, plus, if I multiply that by 24, that's going to be 72 over 96, over, and this is 1, or I should say 96 over 96. I'm adding fractions here. 96 over 96 minus 21 over 96. So 28 and 72 is 100 over 96. Well, and these 96s are all going to cancel. So it's going to be 100 over, and then 96 minus 21 is 75, which is a nice number. And 25 goes into this, 4 over 3. So the tangent of our angle u plus v is equal to 4 over 3. Have lots of kind of messy fractions there, but not difficult to do if you know the expansion formulas. All right, well, so we can use triangles also, reference triangles, to find out what these values are, and without even knowing what the angle is, which I think is pretty cool. Another thing we can do is our favorite thing which is verify. Yes, I hear the applause right now. Verify. All right. The good news is with verifying, I think it's easier to choose the left side, so there's no mystery as to what we're going to do. We don't have to use our cofunction identities and factor out any negatives or do anything wild and crazy on the side. We're just going to expand the cosine of the sum. And that's going to equal the cosine of x, cosine of pi over 2, minus, because the signs collide, the sine of x, sine of pi over 2 equals, and I'm not touching the right side because I'm trying to equal the right side. Now, we happen to know what the cosine of pi over 2 is, or at least I hope we know what the cosine of pi over 2 is. The cosine of pi over 2 is 0. So this will end up being cosine of x times 0 minus the sine of x times the sine of pi over 2. Well, what's the sine of pi over 2? That's nothing more than 1. And so this goes away, and I'm left with negative sine x equals negative sine x. Woo! So we're really happy with that. We just verified our lovely proof, and we're very happy. And we'll make that a bam. Okay? All right. So that's a simple verify. So yes, we can use these identities to verify. What else can we do with these identities? Well, we can use them to solve equations, which is another favorite of yours. Now, before we freak out or panic about this, there is no need, because when you see the sine or a cosine of a sum, the only thing you can do, or what I like about it, is that it tells you what to do, because there's only one thing you can do. You can expand both of these and solve. So let's expand them using the sine of a sum and a sine of a difference identity. So over here, we're going to get, well, I'm going to expand the first one, which will get a sine of x, cosine of pi over 3. The signs stay the same, so it'll be plus cosine of x sine of pi over 3. All right, so that's the expansion of the first one. Plus, now I'm going to expand the second one. That's going to be the sine of x, cosine of pi over 3, minus, because the signs stay the same, the cosine of x, the sine of pi over 3 equals 1. All right, now right away, I'm hoping you notice that this term and this term are the same. So since they're the same, we can just cancel them out because they're opposite signs. And then this term and this term are the same, but we're adding them. So we can say that we get 2 sine x, cosine x, pi over 3, or cosine of pi over 3 equals 1. And the sine, or the cosine of pi over 3 is 1/2. All right, so these twos cancel, and I get the sine of x is equal to 1. Well, where's the sine positive 1? Well, it's up here and on the quadrantal up there. So my solution is going to be x equals pi over 2. But if I want all the solutions, that means infinitely many of them, I can say the solution is x equals pi over 2 plus 2 pi n, an element of the integer set. Okay? Not too bad. So all of this craziness in this equation turns out and boils out down to be just a simple sine x equal 1. So they're really nice problems. And I like to do a couple of them here to get you comfortable with it. So here's another one. Now what's crazy about this one is this negative sign, and we need to watch out for that. That pesky negative will get us sometimes. So what we're going to do is expand this first one, which will be the sine of x, the cosine of pi over 6. Keeping the signs the same, cosine of x, sine of pi over 6, minus, now I like to put a big bracket here so that I know I have to distribute the negative. And when I do that, I get the sine of x, the cosine of pi over 6, keeping the signs the same, minus the cosine of x, the sine of pi over 6 equals 1/2. And now I'm going to distribute the negative. And so when I do that, we get the sine of x, the cosine of pi over 6, plus the cosine of x, sine of pi over 6, minus the sine of x, the cosine of pi over 6, plus distributing the negative, cosine x, sine of pi over 6, equals 1/2. All right, now I want you to notice that again we have a canceling out situation. We have the first term here and the third term here that will cancel. So that goes away. And then I'm left with 2 of the same. So this is going to be equal to 2 cosine x sine of pi over 6 equals 1/2. But what is the sine of pi over 6? Well, the sine of pi over 6 is equal to 1/2. So this is 2 cosine x times 1/2 equals 1/2. And these 2's cancel, and I get cosine x equals 1/2. Well, the cosine is 1/2 in quadrants 1 and 4. And so alpha, let's figure out what alpha is. The cosine is 1/2 when alpha is pi over 6. No, pi over 3. Get the right alpha, Mrs. Muller. Okay, and now I can use the plus solution and the minus solution, and I can say x equals, to get the general, plus or minus pi over 3 plus 2 pi n, and an element of the integer set. Because then that takes care of the plus solutions plus 2 pi n and the negative solution plus 2. All right? All right, then we have one that looks a little different, but it looks scarier than it is really. And this identity includes a tangent of a sum and a sine of a sum. All right, so let's expand it. The tangent of a sum is the tangent of the first one, whoops, not tax, tangent of x plus tangent of pi all over 1 minus tangent of x, tangent of pi, plus, let's expand this one. Now we're going to go 2 on the outside of sine of x, cosine of pi, keeping the signs the same, plus the cosine of x, the sine of pi, equals 0. Now let's plug in what we know. The tangent of pi happens to be 0, so this is 0. That is 0. So what am I left with here? I'm just left with tangent of x, because it gives me tangent in the numerator, and then 1 minus 0 is just 1, so it's just tangent. Plus, the cosine of pi is -1. The sine of pi is 0, so this term goes away, and I'm left with, I really should make this a minus now, -2 sine x equals 0. Okay? So now I have an equation with 2 trig functions. I'd really like to get it so I can factor it or something to use the zero product property. But I want to notice right away I have a tangent in my equation. So when I have a tangent in my equation, I have an implied denominator. And I might have an extraneous solution if the cosine of x is equal to 0. So I'm going to say cosine x can't be 0. That's one of the things that has to be considered when my final solution arrives. So we'll see if we get a solution that contradicts this. All right. So I'm going to change this to sine x over cosine x -2 sine x equals 0. And I notice right away that I have 2 terms here and I have a similar factor. So I'm going to factor that out. I'm going to say sine x times what's left, 1 over cosine x -2 equals 0. So I'm going to set both of these factors equal to 0. Or you could recognize right away that this is sine x times secant x -2. And we're going to set the sine x equal to 0. Well, when does that occur? Well, that occurs on the quadrantals on the x-axis. And so my solution here is going to be x equals pi n and an element of the integer set. Now, I'm okay with that solution because when sine is 0, cosine is not 0, so we're okay with that. All right, next solution is going to be secant x -2 equals 0, or secant x equals 2. And that means that the secant is 2, the cosine x is 1/2, which is the problem we did just a second ago. The cosine is positive in quadrants 1 and 4. I'm going to use the plus and the minus solution here, and I remember that alpha is pi over 3. And so x equals plus or minus here, pi over 3 plus 2 pi n, and an element of the integer set. And so we have that solution. This one looked scarier than it was also, I think. All right, one last example and we're done. And that example is, I haven't done the cosine of a sum and difference yet with this an equation. So let's do this one. Again, the tricky part of this one is distributing that negative. So let's expand the cosine of a sum. That's going to be cosine, cosine, sine, sine, and the signs collide or are co-opposite. Okay, so we get cosine x, cosine of pi over 6, minus the sine of x, sine of pi over 6. And now I'm done expanding the first expression, minus, and I'm going to use a bracket here, cosine of x, cosine of pi over 6. A sign has to be opposite, plus sine of x, sine of pi over 6 equals 1. All right, distributing the negative, we get cosine x, cosine pi over 6, minus sine x, sine of pi over 6, minus cosine x, cosine of pi over 6, minus, so we're distributing that, sine x, sine of pi over 6 equals 1. Now, let's see if we have anything that cancels. Well, it looks like the first term and the third term cancel. So we're going to get rid of those. And then I have a -2 of these. So this is -2 sine x, sine of pi over 6 equals 1. Now the sine of pi over 6 is 1/2. So this is 2 sine x times 1/2 equals 1. And the 1/2 and the 2 cancel. So I get negative sine x equals 1. Sine x equals -1. Now where's the sign -1? Well, the sign is -1 down here in this quadrant. So there we go, or not, it's a quadrantal, sorry. And I can say that my solution is going to be x equals 3 pi over 2 plus 2 pi n, and an element of the integer set. Now, could you have said negative pi over 2 plus 2 pi n? Sure, absolutely. All right, so that's what I know about the cosine, sine, and tangent of a sum. So hope you have a great day, and we'll chat with you later.